Hi everyone. As she said, my name is Julia Ma, and my talk is about generating, extruding, and building, creating 3D objects in code. The title is a reference to Gödel Escher Bach, or GEB, which is a book about math and symmetry. This book inspired the project, which became a motivation for learning 3D modeling. Oh no. There we go. This is the book cover of GEB. It has these letter blocks on the cover that show different shadows based on which direction the light is pointing. And I wondered, can I do this with any 3 letters? How do I even try? How do I make my own letter blocks? So let me start by saying that I know you have many choices when it comes to PyBay talks, and I thank you for choosing mine. This talk is aimed at Python programmers who are interested in making 3D objects. Maybe you have access to a 3D printer and want to use it for a maker project. Maybe you want to add an icon to your talk, like mine. I've got my initials up in the corner over there. It's the M on the left, the S on the right, and the J is kind of from the top view. Maybe you'd like to print 3D custom parts for your work and you don't know where to start. So if that's the case, then this talk is for you. We'll go over the basics of some 3D modeling. And my goal is by the end, you'll be leaving with some tools to write some code that can generate a 3D object. And please feel free to use the Gebify hashtag to be a part of my final demo. So a little bit about myself. I work as a software engineer at Google, where I build features and maintain production systems to serve surveys on the internet. Since everything I do at work is living in the digital world, in my spare time, I like to build physical things, so like little arts and crafts. A few years ago, advances in 3D technology enabled the home 3D printer, and as part of the craze, I also bought a 3D printer. This is the Form 1 that I had at home. But it's kind of, you'd think like, well, what do you make with this thing? Anything that you would think would be convenient, maybe a replacement screw for your IKEA furniture or a phone holder for your car. These are all things that you would have to actually find the 3D model for and then feed it to your printer. So you'd have to either create the model yourself or find someone on the internet who has made it for you. And then printing the object can also be a pain because the print sometimes doesn't succeed, and you'd have to print it multiple times, or it could take hours. So the printer's usefulness really kind of manifests itself in making custom work and art pieces, so perfect for these GEB letter blocks that I wanted to make. But to do that, I would need to learn some 3D modeling. So there are a couple of different paradigms for modeling 3-dimensional objects. There's parametric based, which we'll be mostly talking about today, and then another one called mesh-based or direct modeling. We'll talk mostly about parametric-based, but I'll reference the mesh-based modeling later. So here we'll start in a program called Fusion 360. We model, this is looks like a letter L. The program will show you kind of where the constraints are on the sketch. Here you can see that there are these little T-looking icons. In this case, the T-looking icons mean that these lines are at a right angle. So you could pull these lines back and forth to change the lengths and the height. But the constraint, in this case the right angles, will keep the right angles there. And so some lengths can't exist. So for instance, the 2 short vertical lines must sum up to the long vertical line. Once you have a base sketch, you can then extrude the shape into 3 dimensions. Extruding in 3D modeling means going from 2 dimensions to 3 dimensions. And then you can join it with another shape. In this case, we've added it to a torus. This is a union or addition, and there's a couple other Boolean operations that I'll show you in a couple slides. This process is called parametric-based modeling because you've got a bunch of parameters that really define the sketch. So as an engineer, I found this modeling style very similar to how I think about code. You have a shape of dimensions x and y. You extrude by z. These are just like variables in software. If you decide later that you want to change x, you would expect the whole shape to adapt and update. Since this is parametric-based, you can then specify the relationships between the lines and the curves. So for here, we draw the letter T. Again, you can see the right angle constraints telling you that these are going to be right angles no matter how long or thin the lines are. And on the right, I've extruded the sketch. So let's say you want to change the thickness of the letter. Now you can add some length constraints to the letter. And then when you extrude again, it automatically updates into the new shape. So let's talk some more about extruding. There are various ways to extrude into the 3rd dimension, and different software have different extrusions available. Here's a base shape of the letter T, extruded linearly, as we saw earlier. We can also revolve it around an axis to get this wheel-shaped, which is kind of cool. You wouldn't really expect that like a wheel cross-section extruded in this way would be the letter T, but it is. And if you extrude it rotationally in a different axis, you would also get a different shape. You can extrude it along a curve to get a more complex shape. And some software can also do extrusions between two shapes. So here we have the T and a circle in a different plane, and we've done the loft extrude function between the two. And again, if you update your sketch later, you decide the T needs to be thicker or thinner, the 3D model sketch, will then be able to update. As we saw earlier, we can add shapes together to get a new volume, to get something more complex. Union is not the only Boolean operation that can be done. You can also do intersections and subtractions. So like in my letter blocks, I use subtractions to create holes in letters like the letter B and the letter O. And you can do intersections to do things in 3 dimensions. So here we're doing a subtraction of the word Python in a rectangle, 3D rectangle. To better visualize what each Boolean operation does, these are 2 spheres in a union, the same 2 in an intersection, and then the same in a subtraction. So you can kind of compare and contrast how those work. So this means that the result of what you're trying to model is a collection of pieces. So if you know what you're trying to go for, you can start there and work backwards. So for instance, if you're trying to model a screw, you can just break the 2 pieces up. You've got the head and the body. The head could be a cone, and you've truncated part of it off. And maybe you subtract a rectangle from it to get that slit. And then maybe the body, if you do like a cross section of it, it looks like a circle with a tab at the end that's then like spirally extruded. And I'll show you this in our demo. So with these fundamentals in mind, I'll go over a couple of the tools that I tried and what I thought about them. These are 3 of the big ones that are out there: Solidworks, Inventor, and Fusion 360. Solidworks and Inventor are really commonly used in industry, but they're expensive, and they're only available for Windows. Fusion 360 is also available for Mac, and those are where all my previous screenshots are from. Also, there's a hobbyist version of Fusion 360 that's free. That's why I use that one. So this is a screenshot of the workspace of Fusion 360, and you can see there's the tools. It kind of tells you the parameters that you've got available to you, and in this case, it's like where we've extruded it in the screenshot. So my first letter blocks I created in Solidworks, which looks very similar to this. And as you can see, I managed to print a couple letter blocks. It was a little hard to visualize, but the left one is a K, a P, and then a J from the top view. This one is PTL. The problem is that these are very labor intensive, and I was drawing these letters by hand. So especially for more complicated letters like the K and the P, I was doing a lot of math in my notebook, trying to figure out the angles and the curves and the shapes, and I didn't actually know if the resulting 3D object would be a printable thing, if it would be one volume. So could you do EHM or W, Q, and V? Are those impossible shapes? And I wanted to be able to rotate the letters in the plane to try different combinations. And to do that, it was a very labor-intensive thing to do in software like SolidWorks or Fusion 360. Another popular software out there is Blender. This is a screenshot of the workspace in Blender. Blender is very powerful, open source, free, does a lot of cool things like animation, even has a game engine. But at my beginner level to 3D modeling, I found Blender's learning curve really high. It's also not exactly parametric based, it's direct modeling or mesh based, which basically means that each point that you model is a floating point in space. So you're creating surfaces out of all the points. But if you move one point around, the constraints that you saw in parametric modeling don't necessarily apply. So you could create really bad 3-dimensional objects, you can create really unprintable things. In general, I found Blender to be better for more artistic things, so this is actually something I managed to make. I was interested in platonic solids and wanted to play with the math behind them. So the number of vertices in an octahedron is the same as the number of faces in a cube. So to do that, I modeled the octahedron kind of trapped within the cube. This is actually the result of the 3D printer pictures that I showed earlier. I've removed the support structures, so the octahedron actually moves freely within the cube, but doesn't fall out. There's a lot of 3D modeling software out there, and these are only just the ones that I've heard of. Like anything else, picking the right tool can be half the battle. But 3D modeling software can be intimidating for someone who just wants to make some fun objects for their 3D printer. Programs like Solidworks and Blender have a steep learning curve, and creating simple objects can take a lot of time, as I realized. I wanted to be able to try the different rotations. I wanted to go through all the combinations of all the letters, and how else can I do that except programmatically? Before I continue, I should note that a lot of these 3D modeling softwares do have Python APIs. For example, Blender has a very integrated Python API, and it's very well documented. It even has its own Python terminal inside. And a lot of the features can be scripted directly from Python. However, because very similar to kind of how Blender approaches things, it assumes that you have a mouse, that you're working on a screen, that you're looking at a three-dimensional object. It assumes things like cameras and shading and all sorts of other features that I didn't really understand. And I felt like the Python API kind of came from that point of view as well, and it made it really hard for me to figure that out. At some point, OpenSCAD came into my knowledge base. I'm probably going to call it OpenSCAD during this talk because it's faster. And it had been recommended to me by multiple people. I liked it because it's a script-based modeler. It's free. It's parametric. It's available on all the popular computers. You can define variables and functions. There are math functions and flow control, but it's not really a fully object-oriented language. And the online documentation is pretty good, but that means you're still learning a new language. So if you're trying to do something more complicated, it can be a little hard to do that, and it's just another language for you to learn. This is a screenshot of the OpenSCAD environment. The left side is the editor where you can edit the model that you're trying to make. And the right side is the model where you can pan and zoom around. So what can we do if we don't want to learn another language? Introducing OpenPyScad. I found this library. It is a Python interface to OpenSCAD. Allows you to write Python code, which creates a SCAD file, which you then open in OpenSCAD. And because it's Python, then you can harness the full power of Python. So here we have 2 lines of Python code, and this creates a 3D object. The polygon function takes in a list of points to create a polygon, in this case 4. You then call linear extrude, which does what it sounds like, to a height. You can twist it, which just twists it. And then you call dot right at the very end, which spits all of that out into the SCAD format. Here it's going to go right to example.scad. You open that SCAD file into OpenSCAD, and voila. So to me, the difference between these tools is that here, OpenSCAD feels like it's driven by the programming experience rather than the visual experience. And so the Python API kind of comes from that as well. So this is the workflow that I just talked about. You start on Python, do everything you want to do in Python, call dot right to a SCAD file, open that SCAD file in OpenSCAD. If you're happy with your results, you then export it to an STL, which is a file format that describes 3D models as a series of triangles. And then you send that to your favorite 3D printer, and hopefully it prints out what you have been looking for. So to get started, install OpenSCAD, install OpenPyScad, and now we're going to demo the making of the screw. Cool. So, oops, not there. There. All right, so let's start with the body. We call a circle function, which takes in a radius. And just to demonstrate exactly what this does right now, we're going to do a dot right on this. And then down here, we call Python on that file. Where's my mouse? And now there's a file called OpenSCAD, a demo.scad, which opens OpenSCAD, and there you have a circle. Cool. Let's continue. So let's make a thread. So if you think about what the body of the screw looks like, what we're going to do is we're going to do a cross section of it and model that cross section and then extrude that. So the cross section to me kind of looks like a square. That's like a little notch off to the side of that. Yep, that's right. There's the thread. And then to do that, we add them together. And then call linear extrude. Linear. Yeah, I'll fix that. Thank you. Cool. And it automatically updates the file because OpenSCAD actually looks at the file. Any changes to it, it automatically renders it. So here we have the body of the screw. To do the rest of it, I'm just going to copy and paste over some of the things. So the head of the screw, we're going to model it. We're going to model the head like a cylinder. Equals 20, equals 40. Okay. And then we're just going to do this. So the head is a subtraction here because we want the slot to cut out the notch. And we're just going to overwrite that file. And there's the head of the screw with the notch. So I was able to model all of my letters into Python code. That's the geb.py up there. I'm not going to show you the code for that, but I am going to show you the result of that. So what are your initials? AP. AP. I'm going to add just like an X at the end because I need 3 letters here. Hold on. And we're going to render that. The rendering takes a few seconds, and it randomly picks some orientations on this, but here we have an X, we have an A, and we have a P. Cool. So let's go back to present. And you guys don't need to see that. So one of the things that I ran into while doing OpenPyScad is going from Python 2 to Python 3, actually. So here's a simplified version of the letter O. We give it 4 points for the polygon. We just draw a square here instead. And one of the things you can do is you create all these holes. This, for instance, it takes a list of all the points for the entire shape. And then polygon takes in a second argument, which you can tell which are the outline and which are the holes. And I used the range function to basically to do the indices into that polygon list. So here, this is Python 2. I call dot right on that, and I get this approximation of the letter O. When I went to Python 3, I was getting an error because the range function became lazy in Python 3. And so that's actually a very simple fix that took me way too long to figure out. Is just to force that into a list before you call OpenSCAD on it. So then just to recap, this is the flow that you go through to generate a 3D model. You're going to write all your code in Python, export it to a SCAD file, open it OpenSCAD. If you're happy with how it looks, call render on it, zoom around, pan around. You can make your edits back in either your Python file or directly in OpenSCAD if you want to mess with the terminal a little bit there. And then when you're happy, export to STL, send it to a 3D printer, and print it out. But then the question is, why would you do this in Python? Why not just learn OpenSCAD and do it in OpenSCAD? Well, Python comes with this full programming language behind it, has a lot of power, and you can do all sorts of really crazy things. It's whatever you want to do, because it's Python. So let's say you want to build this crazy thing where you have an if this then that applet that looks at this hashtag on Twitter. Whenever it sees that hashtag, it sends an HTTP request to this Flask server that you have on your home server. The Flask server takes that tweet, sends it to your geb.py file, does some processing on it to pull out some letters to make into a 3D object, calls OpenSCAD from the terminal, which you can do, which is kind of cool, and then export to an STL without ever having to actually open the program itself. And the last thing it does is it tells this Node server, and we're using Node because we want to end up using WebSockets, and it was easier to do it that way, to open it into a browser to see this. And so Yogi Mark, whoever you are, sent a tweet, and I created a 3D object out of that. So yeah, thank you. So there are a couple of things that still need work on this. The 3D objects that it creates are not necessarily going to be good objects. You still kind of need to visually inspect it before you send it to the 3D printer. For instance, if you scroll down here, there's bound to be one of these, maybe not, that have like floating blocks in there because one of the letters cut out too much of the other letter, and so now you have like 2 or 3 pieces floating around. So that's not going to work. And the OpenSCAD program will tell you if there's a couple errors. And the main error that I ran into is it'll tell you if your shape is not a two-manifold, which basically means it's not enclosing a volume. So this happens sometimes when your letters intersect at a specific line, like a specific plane or a point. So the 3D printer might be confused over that. And another thing that, so you can either fix that by either, adding a little bit of wobble, not wobble, but like error to your values so that it doesn't cut exactly on the points themselves. And if you run into that and you don't know how to fix it, you can also use a program called MeshLab, which will fix it for you before you send it to your printer. But the downside about OpenSCAD is it won't tell you actually if it is become 2 blocks. That you're just going to have to visually look at and see if it works. And yeah, that's what this will do for you. So I have some blocks up here if you guys want to check them out. And I'm happy to answer any questions. Thank you for coming. Yes?
Is there an easy way to add like texturing or any textures to the object?
That's a good question. I'm not sure about that because I actually don't know. Oh, sorry, I'll repeat the question. The question was if there's a way to add texture. And the answer is I don't know. Yes?
This is a shot in the dark, but is there any tool that can convert SCAD files and generate the Python code from that file?
Ooh. The question is there a tool that can go backwards from an SCAD file to the Python code to generate that? I also don't know, but that sounds really cool. I'm sure there is because the OpenPyScad, I think, is really just compiling it. It's like it runs the Python code, and like whatever that is, I think it's like a 1-to-1 translation of what gets spit out. If you look at the actual OpenSCAD code that your Python code is generating, you will see like the keyword terms like circle and cylinder and those in there. And they take, hello. Yes, the answer is I don't think so. Yeah. Any other questions? Cool. Well, thank you.